Hello everyone, and this is Mohammad Abdulaziz, and that's the fifth sheet of the Function Data Structures course. So today we'll try to be covering some reasoning about chains of equations. So reasoning about them in Isabelle. And I'll also try and cover case splits over data types, which were both explained to you in the lecture number 5. So I'll start by the first question on the sheet, the first exercise on the sheet. But before I do that, I just want to tell you that we shouldn't be using sledgehammer in these exercises, because I want you to learn how to find theorems about addition, multiplications, etc. yourself, and also how to use the different automation methods for numbers, for proofs about numbers in Isabelle. Okay, so firstly we need to import complex domain. And whole library 3. Okay, so now the first exercise is we want to show that 2 to the n is always strictly smaller than the factorial of n if n is strictly greater than 3. So that proof will be by induction on the natural number, as shown in the sheet. But I would like to show you first induction on paper, and then how we do it on Isabelle. Okay, because I just want to make sure that all of you understand the meaning of induction and the correspondence between the induction in Isabelle and pen and paper induction. So what we want to prove is, we'll write it informally just to show the analogy between the Isabelle induction and the pen and paper one. Okay, so I want to show that 2 to the n is always strictly smaller than factorial of n if n is greater than 3. Okay, so if we prove this on pen and paper by induction, so by induction on n, so we have 2 cases. The base case, okay, which is when n equals 0, okay, and in that case we basically want to show that if in the base case, i.e. in other words when n equals 0, you basically substitute all occurrences of the statement that you want to, all occurrences of n in the statement you want to prove with 0. So basically what we want to prove here is that if 0 is greater than 3, then we have 2 to the 0 strictly smaller than factorial of 0. And that of course will be true because the assumption here is going to evaluate the false, and false implies everything is always false. Okay. Now the step case. Okay, so this is what does it mean, and kind of not in Isabelle. So when I say the step case in such a proof, what I mean is that informally we assume that the theorem holds for an n, okay, and then show that from this, if we assume that the theorem holds for n, we can show from that the theorem holds for n plus 1. Okay. So in our case, let's instantiate that. So we assume that the theorem holds for n, which we call the induction hypothesis. So we have 2 to the n strictly smaller than n factorial if n is greater than 3. Okay, and we want to show that from that, if n plus 1 is greater than 3, then 2 to the n strictly small is 2 to the n plus 1 is strictly smaller than n factorial, n plus 1 factorial. But what that so what we want to show actually has an assumption of its own, which is, let me just write it. So so given that we want to show um, 2 to the n plus 1 strictly smaller than n plus 1 factorial if n plus 1 is strictly greater than 3. Okay, so when the theorem that you want to prove has assumptions of its own, which come from the fact that this also has an assumption, we call this so this is the assumption of the statement that I want to prove. We call this the assumption. We call it the premise. Okay. So you have an induction hypothesis and you have a premise, and you want to prove from both of them the conclusion or the goal here. Okay. So let me show you the basic steps for that proof. So like in pen and paper, we would say from the premise from the premise we can okay, so we actually need to split it into 3 cases. So the first case is if n 2 cases, sorry, if n is strictly greater than 3 and if n is equal to 3. Okay, so let's say let's first consider if n is strictly greater than 3. What do we have there? What we have here is then from the induction hypothesis we have that 2 to the n is strictly smaller than n factorial. Okay. According because n strictly greater than 3 is an assumption of the induction hypothesis there. Accordingly, from that we can then say so from what I have here, then we can say then if we multiply both sides by 2, we'll have 2 times 2 to the n is strictly smaller than 2 times n factorial. Okay. For n factorial plus n factorial. Okay. And okay. We also have we have that this is that that n factorial plus n factorial is strictly smaller than n factorial plus n times n factorial. Okay. Okay. So we have that 2 times. So we can say on the paper, pen and paper, thus 2 to the n plus 1 is strictly smaller than n factorial plus n times n factorial. Okay. Now, from that, we can then show that what we wanted to do is what we wanted to show that. Okay. So does that follow from this? Yes, it does follow from this, just from the definition of factorial, because this thing. I mean, we can actually, let me just continue that chain. Okay, so we have that this is strictly smaller than that, and we know that this one is actually equal to just n plus 1 factorial. Okay, because what let me just explain that in more details, so that I make sure that you understand the details. So we have here that n, this is equal to n plus 1 times n factorial, which is equal to n plus 1 factorial. Okay, thus we can say we have 2 to the n plus 1 strictly smaller than n plus 1 factorial. Okay, and if n equals 3, we have, okay, so if n equals 3, then we have our, then just by evaluating 2 to the n plus 1 and n plus 1 factorial, we have our goal, or we have proven the theorem for that case also. So basically it will be like 2 to the 4 is strictly smaller than 5 factorial, and that is obviously true. And okay, and before actually you do these cases, like in a pen and paper, we can say firstly that we know that n equals 3, or n is strictly greater than 3 from the premise. Okay. Okay. So we know that we only have those two cases from the premise, which is that, and then we prove the theorem for each one of the cases separately. Okay. So now let me show you how to do that in Isabelle. So so firstly, when you're writing numbers, just make sure that your types are correct. So so n greater than 3. To the n. Okay, so that's the theorem statement. Okay, and then we do again by induction on n. Okay, and then the first case is by O2, and that is equivalent to here in the paper. To this case, okay, because we know that 0 is always going to be not greater than 3, thus anything can follow from there, including what's the conclusion. And the second case here, we have that, okay? So now, firstly, I want to prove from the induction, from the premise, as I said, I want to show that we have here this disjunction. So n equals 3 or n equals or n is strictly greater than 3. So the way we do that in Isar or in Isabelle, in the Isar language, is that we say then. So n equals 3 or n strictly greater than 3. Oh yeah, you can have, or you can say just hence. Okay, so when I say then something, then have something, like what we have here, or so here we have then show, but we can also have then have something, which is equivalent to hence. What that means is that assume using the previous fact, which here happens to be the induction hypothesis, and that and the premise, I want to show this disjunction, but I will just show you precisely how to access the different components of the induction hypothesis and the premise. Okay, so in our case, we want to show this using the premise. Okay, as I did on the paper. So what that means is that using suc the prems. Okay, so these are the premises in general, which are the assumptions. Okay, and we say using the premises, I want to show that theorem. Okay, so by O2, and then I want to show I want to do my proof to show my actual goal. Okay, and the actual goal was generated. So here, when you do induction, you have this schema, and then you click on it, and then you get a template for the proof. So here, now we have a disjunction, and we want to do this different cases, to consider different cases in the proof. Okay, so the way you do that is firstly by proving the disjunction, and then saying then show whatever you want to show, or then have whatever you want to prove, and then say proof. And that will automatically, when it sees that you have a disjunction, and then you want to prove your goal based on that disjunction, it will split it for you into two different sub-goals. Okay. So the first sub-goal is we do it as follows. So we assume n equals 3. Okay. And then from that, we try to show that goal. Okay, but of course that will not just be one step, but I just want to copy the goal first. Okay, so what we want, I will just do the steps that I did on the paper. Okay, so here the first step is from the induction hypothesis. We say that I will actually start like what I did in the paper with the case when n is greater than 3. So here you have two sub goals. Okay, and what usually when you have a sub goal, a sub goal that is of the form something meta implies something else, what you do is you say assume that, and then show that the conclusion of the implication. Okay, so here I'm assuming this, and then I want to show the conclusion, but in the middle there will be many steps. So the first step is so we need to use the fact that n is greater than 3, and also the induction hypothesis. What we do here is suc.ih. Okay, so that those two facts assume this from the assumption that n is greater than 3, and then in the induction hypothesis that we have, which is suck.ih. Suck comes from that, and ih is the induction hypothesis there. So we have that 2 to the n is strictly smaller than factorial of n. Yeah, so what we need to do here is to fix the type of the 2 to not, and then that will go through well. And then we can do the next step in our proof on the paper. And that step is this one. Okay, so 2 times 2 to the n is smaller than, so I can just do 10. Okay, actually before I go there, I just want to show you something to make sure that you know it. So you can also say, instead of letting sim combine both of those facts by itself, you can also say that we can instantiate the first assumption of the induction hypothesis with this GT, and then we get just the conclusion of the induction hypothesis, and then we have what we want. And then in this case, you actually don't need to say by sim. You can also just say that if your assumption is the same as your conclusion. Okay, so leave it as it was. So all these are variations of doing that. So I can say also then have something, which means that I want to prove this new fact, knowing that in my assumption, knowing that I have proven the previous fact. So I want to prove this fact using this fact, basically. So here the new fact is 2 times 2 to the n is smaller than fact n plus fact n. Okay. And again the types. You can actually change that into hence, and that is exactly the same thing. So hence is just a shorthand for then have. Okay, and so here we did the second step. I just want to make sure that you understand. So with have is different from then have in the following sense, that with takes the previous fact plus a list of theorems after, a list of facts after it, and then you use all of those to prove what you want to prove. Okay. Then have only uses the previous one. This is also equivalent to saying then have using that, or hence using that. Okay, so I hope you get the taste for it now. So now the next thing is to show that this step. Okay, so I will use the chain of equations reasoning to do that. So I would say also have fact n plus n okay. Let's do some step here. So C by sim happens. So it doesn't work. But actually, in order for this to work, n has to be strictly greater than 0, which we forgot to say here. So we have that from the assumption GT. Don't forget that. So GT, it says n is strictly greater than 3, not just 0. So like that. And let me just make sure that you understand this. So when you say also have something, and then dot dot dot, that dot 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 is the right hand side of the previous equality or comparison. Okay, so here in this case it is fact n plus fact n, so that's why this thing there is equivalent to that actually. Okay, so this is the dot dot dot. Then you can say again also have dot dot dot. This time the dot 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 will be the last one. Okay, so we can here say also have that this is the same as fact of suc n. Okay, and then we have that, and then so what's the next step there? So now we're done with that, and then we want to just do the final step. So do we say finally show the goal but with the right types. So we have here, when we say finally, it basically does the following. It says it relates the left hand side of the first thing in the chain of equations to the right hand side of the last thing in the chain of equations, and it relates it with that, with this operator here. Okay, so here this is the less than this time, and okay, so now we can just try and do that with sim. Yeah, it did work. But let me just show you another thing as well. So if we do this to be plus 1, yeah, it also works. Yeah. So in any case, sometimes, yeah, I think we'll need it in the next sub goal. So the next sub goal is when n equals 3, and then we need to show that. So assume show. So then show that. Okay. So you can also replace then show by thus. It's the same thing. Okay. So I will just say by sim, and yeah, it will not work. So the problem here is that sim doesn't know what fact of 4 is, because factorial and all recursive functions defined on natural numbers are defined on either 0 or suc n. So in other words, they always match for suc something. And 4 is a numeral, well, it's a constant that is equivalent to suc 0 or suc 0, but it's not the same thing. So you need to basically unfold this 4 to be suc 0. And the way you do that is by, I think it's called numeral eval one moment. So yeah, it is actually mat eval numeral. So that's the name, sorry. Yeah, eval mat numeral. So let's see what's wrong now. No, it's numeral eval mat. Can square. No. Yeah, I think I knew it. The problem is with the types there. So that's it, yeah. So I've been warning you about don't forget to set the types, and I forgot it myself. Okay, so that's the thing. So let me just recap that. So here I was showing you how to do induction with these are. So induction, and you do the induction, and then it gives you a proof template, and then you click on it, and then it gives you that. The first case is the base case. The second is the step case. In the step case, I was showing you how to use ISAR to prove things in which you have different cases, and what that means is that if you have something and you have different proofs for different values of that thing, then what you can do is prove that the n, for example, here will only take us will only fall under specific ranges of values. So here it's either equal 3 or strictly greater than 3, and then you say then show whatever you want to show, or then have whatever you want to have, and then if you say proof, it will automatically split the proof in the right way for you, and then you can do that. So this is the chain of equations, and this one here shows you how to deal with numerals and and transform them to natural numbers. Okay, and then you just do QED and then QED of the lemma, and then you're done with that. So now let's start with the second exercise. So here we have what we have is we need to define a function that higher order function that given another function it computes, and a natural number it computes the summation of that function applied to all natural numbers from 0 up to the natural number argument. So let me show you an example of what that is, just to make sure. So, well, I think it's actually clearly written there. So basically you want to prove a sum 2 of f of n that gives you that, okay? So let me just firstly define it, okay? So sum 2 So it takes a function from natural numbers to natural numbers, and a natural number, and returns a natural number, okay? So this one will be recursive over the natural number argument, which is the second one. So it will be, in this case, will be sum2 f of 0 equals f of 0, and otherwise sum2 f and n, okay? So that's the function. So let me just try and so for instance, if that function is id, so here you have 0, and this is 1, and this is 3. Yeah. So it is the function that we want. Okay. So let me just now go to what we need to prove, which is the more interesting part. So basically, I want to show that this squared is equal to that cubed. Okay. So again, let's write that theorem statement. So firstly, we'll probably need this lemma there. So I'm taking it as it is from the sheet, and you will see why when we're doing the proof. squared is the lemma. Okay, so we need to prove this. So maybe I should also try and do the proof on the paper. So let me just set it up first actually, and then we'll do the rest of the interesting part of the paper, okay? So again, it will be by induction. So you press Control I to do the automatic indentation, okay? So by induction, and now it's in. So let me just let me do the proof on the paper first, and then we can go back to Isabelle. So what we want to show is the summation of f of I squared equals the summation of summation of I squared equals the summation of I cubed here. Okay, so this is inside, and this is this is squared. The square is outside of the whole summation, and this is inside each I. So I equals 0 again to n. Okay, so induction hypothesis will be we have that for n, so we have the summation of I from 0 to n squared equals summation of I cubed from I equals 0 to n. And we have no premises here because the theorem doesn't have any assumptions. So that's basically we will need to manipulate that directly. Okay. So what we want to prove is the goal is to show that I to 0 to n plus 1 from I equals 0 to n plus 1 squared equals summation again cubed from I equals 0 to n plus 1. Okay, so we want to do a chain of equations, obviously, and so here we're going to start with showing that this thing here, so unfolding it, just simply unfolding it, so we will say this is equal no, actually we can't start, no, we have to start by unfolding this until we reach that. Okay, so that's the goal, and then I will start. This is the proof. Okay, so sigma from I equals 0 to n plus 1 whole squared. What is that equal to? It's going to be equal to I the summation So this should be equal to the summation from I equals 0 to n of I plus n plus 1. Okay, so the main reason we're doing that, or the reason we're doing that, and then all squared, is that we are trying to get this term to match what's in the induction hypothesis, and then substitute the part of this that matches that with this, and then hopefully manipulate the rest. Okay, so the main idea is basically you're trying to show that this term is that plus or multiplied by some other things. Okay, and then you're going to replace that with this and then manipulate the other things. Okay, so here the first step to do that is this, and then the second step is to just do the binomial expansion of that. So here, so I'll just say this is by the definition of this sum, and then this one is going to be the binomial expansion. So from I equals 0 up to n I squared plus 2 times the summation that we have multiplied by n plus 1 plus n plus 1 squared. Okay, and this is just binomial expansion. And then now we can replace that with this using the induction hypothesis. So we can say this is equal to I equals 0 to n I cubed plus 2 times summation of I from 0 to n multiplied by n plus 1 plus n plus 1 squared. Okay, so this one is just using the induction hypothesis. Okay, so now we did what we wanted, and now we want to and the last thing is to manipulate this to get to show that basically this whole thing equals n plus 1 cubed. Okay, and then okay, so how can we show that this is equal to n plus 1 cubed? We will just write this firstly. So now how can I, so we must use the lemma that we proved, that I copied to change this thing. So okay, so let me just go back one step there, or write the lemma here up there. So the lemma that we proved in Isabelle that was, so it basically says sum 2 of ID. So this is the same as ID. So the lemma says that the summation effectively, this lemma says effectively the summation of 2 times the summation of I from I equals 0 to n, okay, equals n times n plus 1. Okay, so now we can replace this part of the summation with n times n plus 1. Okay, So n 2 times n times n plus 1 is n plus 1 squared. Okay, so using, I'll just call this lem. So this was proven using lem. Okay, and then the last step is to show that this is equal to n plus 1 cubed, and that's obvious. So this now we're going to rewrite it into n plus 1 cubed, okay? Just by evaluating n plus 1 cubed. So let me just well, I think you can do that yourselves. And then lastly you can say that this is equal to, from I equals 0 to n plus 1 I cubed, and that's it, using the definition of sigma, and that should be the end of the proof. So now we have written that, and now I will just do that in Isabelle, and then show you how to do the separate reasoning steps. So first, so let me just use Isabelle. Yeah. So now I will. So first of all, look here. We want to do this binomial expansion, okay? And to do that binomial expansion, we need something called algebra sims, which is a set of simplification rules that are useful for algebraic manipulations like computing the binomial expansion. So I will add that to the sim set because in fact this is useful, not just in this step but in other ones as well. So we want these algebraic manipulation, algebra sims, okay? And now I will just show the thesis case. So yeah, that should be called induction actually, because then now we will have the nice names. So that's a good thing, just as a side note. So if you say induct only, it's the same as induction, but you don't have, you will not be able to have things like IH and prems like the ones there. Okay, that's the difference. So so now I will say showcase. So no, sorry, I will just say first let's start with the steps. Okay, so I will say I'll take that and do so that equals what did we have there? The right hand side. Just this one. Okay. This should be okay. Sorry, that should be suck in. And then, well, no, sorry, we're going to use also. So the right hand side of the previous equation equals the binomial expansion of itself. And what is that? So I'll do the binomial expansion manually. So here squared and squared also have, and then in the middle we'll just have a term 2 times both of them multiplied by each other. So this should follow by sim. Just make sure that the types are correct. Well, actually, I don't think that the binomial expansion is in algebra sims. So let's see. I'll just see if we have an answer of find theorems. So something plus something squared equals, yeah, that's the binomial expansion. Power to sum, so sim. And part to sum. So I think I know why. It's because when we write suck n there, we have some, so let's just look carefully into that. So look, when the left hand side was simplified to this undesirable form because simply the theorem about this theorem about the binomial expansion didn't match it, because the theorem needs some before the simplifier rewrote with that theorem, power to sum, it rewrote with something else in the set of algebra sims that which I don't really know, but I guess that this is what it is, that changed the left hand side into that thing. So usually this happens when you have a suck n, and then, as I said earlier, a lot of the recursive functions that are defined on suck n. So here, okay, so a lot of recursive functions, or all recursive functions, the natural numbers are defined on they match for the pattern suck n. So if you have a suck n there, you might have an undesired rewrite. So what happened here precisely is that it rewrote the definition of plus, which is the addition, and addition is just is defined recursively on suck n. So before it did the power to sum, before it did rewrite with the power to sum, it rewrote with the definition of addition, because the second argument was a suck. But when we made this into an n+1, let's see what happened. So, well, it's still as it is. So what we have here is look at the left hand side carefully, and then you will find the problem. The problem is that it couldn't rewrite with power to sum because it look here, we have a suck outside and then the addition inside, and then all of it is raised to the 2, while in order for you to use power to sum, remember the theorem here, you have to have the addition just in the parentheses that are before raising the power. So what happens here is that basically what we have the definition of addition being unfolded before that is being applied. So one way to avoid that is just to tell the simplifier to only simplify with power to sum. Okay, so not to apply the definition of addition. And so because the definition of addition is defined in a way such that x plus suck n equals suck x plus n, and that's what happens. And then this is rewrote before the power to sum lemma. Okay. So now that's the binomial expansion. So let me also write that in a more palatable way. And remember that this might lead us to need eventually to use the net eval lemma, net eval numeral. Okay. So now the next step in the proof is this one. Okay. So we need to apply the induction hypothesis to transform that thing. Okay. To transform the first term. Okay. So also have dot equals that thing, but I want to replace that one with that. Okay. Sorry. So that is it. Yeah. Which is that basically. Okay. And that should be doable using suck the induction hypothesis sim. Okay, so the induction hypothesis quite simply is the theorem on n. Okay, and then we have that. Then we need to do the next step, which is this one, which is to do the rewriting using the lemma. So we say also have so I'm going to replace that with that. Okay, so we'll copy that and then replace it using the lemma. So that should be replaced by n times n plus 1. Okay, using sum of naturals by sim. Okay, and then I think this is the last step. Which is that to transform the second term into n plus 1 cubed. Okay, and that should be a consequence of the algebra sims. I hope. Maybe we'll need to break the 3 using nat eval. Let's copy the theorem name. Eval nat numeral. Let's hope that this is it. Okay, because the definition of power uses suck, matches against suck n, and we have here a numeral 3, so we need to unfold it into suck 0. And then we just say So I think that's it. So finally, show this case. So I think that's precisely what we want to show. No. Yeah, we just have, no, we still have one more step. I mean, it can be just done here by simp. Or we can also do it as a separate step there. And then say that this is just plus 1. Now, okay, so now we might want to change this to suck n. So just match the goal. Okay, and then now we have exactly the goal that you want to prove, and then if you have the goal in your assumptions, you can just use this dot, okay? So that is the second is our proof that we're doing for today. So now let's start with the third exercise. So remember last week we came up with we defined a function that computes that given a certain natural number, it gives you the set of all trees whose height is exactly that as the given natural number. Sorry, is exactly that or smaller. Okay, that was the function. So now I'll just copy the definition and the proof for it. So at the time we only proved that this function is sound, as in any tree in the given set by the function will have its height upper bounded by n. And now we want to show that this function is complete. So what that basically means is that if any tree has it's the contrapositor of it's the opposite of the soundness in this case. In the implication is in the opposite direction. Okay. So if the tree has a height that's less than or equal n, then it's going to be in the given set. Okay. So let us look into the proof. So it seems like we have a problem there. So I think the problem is in the definition here. This enum of 0 should actually give us a singleton set that has only a leaf. So that's actually a problem that I just found out. So basically the other definition is also sound, but it's not complete. So the definition we did last time is not complete because of this specific counterexample that will be found shortly. Okay, so if you're given 0, okay, the function enum will give you the empty set, but it should give you the tree whose height is less than or equal to 0, which is the leaf, and that's why we need to do that there. Okay. So now let's do the proof again and see what happens. So this proof, I can just spoil it for you. It will need a case split on the tree, a type-based case split. But let me show you why firstly. Let's try and. So basically, basically the so we're going to split. We'll need to split cases on T, and that will give us two cases. So k can either be a leaf, and then this will go by auto, because leaves will always be in enum, because enum of 0 is a subset of enum of any other number. And the other case is when T is a tree with two subtrees, like this one. Okay, so then you will have the two subtrees will have height less than or equal to n. So both of the subtrees will be in the enum of n. And then we have here, look into this assumption there. We have that if some left subtree is an element of enum, and then for any tree that is equal to this left subtree and any right subtree, the right subtree will not be a member of enum. Okay, and then but remember that from the induction hypothesis we will have that both subtrees L and R will be in the enum, because the induction hypothesis will apply to them, and accordingly we will have a false in our assumptions. And if we have a false in our assumptions, that means that we can prove any theorem out from it. Okay, so let me show you how to do that with ISAR and with apply style, and then I will show you how to do it with ISAR. Okay, so firstly, okay, so now we have one goal. Well, actually, let me show you this. So there's this keyword sub goal, and that so when you do induction, you have two sub goals. Okay, if you want to focus on one sub goal, you can the first sub goal in the list. You can say sub goal, and then you have to call the variables a name. So here, for example, the variables on which there is a quantification there. So here we have for all t. Then we will just say the first sub goal for t. Okay, I want to apply auto. And then that sub goal is done. Okay, and then another sub goal, but this one has quantification over n and t, so we'll just say for n and t. Okay, and then what I said I wanted us to do is to get the to do a case split on t. So it actually is clear why we work in the sub goal before we do the O2 element. Okay, because remember, when you say sub goal on the first sub goal here and then say apply O2, this only applies O2 to the first sub goal, but not to the second one. So the second one is still fresh here. So when you do do a case split on t, you will have t is either empty, and as I said, empty is an element of any enum, and or t will be we will have two subtrees, and both subtrees will be in enum of n. And from the definition of enum of suc of n, if two subtrees are in enum of n, then a tree formed by those two subtrees as two of the subtrees will be in enum of suc n. Okay, this comes from the definition there. Okay, so let me show you how you do this. So apply cases on t. So this gave us two sub goals. The first one when t is empty, and the second one when t has two subtrees. Okay, and then you apply auto, and it's gone. Okay. So now we'll show you how to do that same proof, but in ISAR. Okay, that's an extra exercise. Okay, so you have proof, induction. Okay, and then this is the template that comes out of induction. So the first case is equivalent to the first sub goal, that one, and the second case is equivalent to that sub goal. Okay, so here again I want to do it by cases on t, so we can just say apply cases of t. Look here, so the induction hypothesis, the premises talk about this t. So instead of having to say for n and t, the premises already talk about n and t. So we say cases on T and then apply auto and then done. Or you can also say by cases of T and then done. So when you have only two commands, when you have only two apply commands, you can say by the first one in brackets and then the second one like that. So that's our version of that proof. So now let's go to the fourth exercise. So here in this exercise we need to pretty print binary trees, okay? And let me just show you what that is. So we need to define a function that given a binary tree does the following, okay? I'll show you on the paper there. So so let's say we have this tree. Okay, I want us to pretty print this tree in the following way. So I want to print a list, okay, such that every element in the list is equivalent to one node in the tree, and this list and like each of the elements of this list will either start with an n, which means that the node is an inner node, or l, which means that the node is a leaf. So, for example, in this case, we will get n2. Okay, so we start from up, we start from the root, and then go down in the same way, like in depending on the rank, on your rank in the tree. Okay, so we start with the nodes with the closest to the root, and then go down until we reach leaves. Okay, so n2. Okay, and then that node will have two subtrees. The first one is this one, the left one, so it will also be an n1. Okay, and then we need to finish the whole subtree first, and then go to the second one. Okay, so node n1 is an inner node that has 1 as data in it, and then its left subtree is a leaf, and its right subtree is a leaf, and then there is n3, and again a leaf and a leaf. Okay, so in order for us to get that, we'll define a data type that covers the two cases of leafs or inner nodes. Okay, and let me just copy the data type, and let me just do it. Okay, so that's the data type, and the function, the pretty printing function, will be this way. Okay, so it takes a tree and gives you a list of those of this data type. So either a leaf or an inner node with some content in it. Okay, and that function should be like this. So pretty should be recursive on the tree. So pretty of a leaf equals L. Yeah, singleton list of L, of course, because we were opening here list. And if it has data in it, so node LAR, then we will get NA cons pretty L, and then appended to pretty R. Okay, so let's try that on the tree. So we have a function, so pretty, and then I have a node, and then that node has so let's just change that type. Okay, so that's clear. Okay, and maybe we can also do the other trees. This is the 1, the 2, this is the 3, let's see. So it looks exactly like the one on the paper, okay? So that is the function. So now, I will show you two things. So, first I will just tell you the purpose of this exercise. In addition to defining this cute function, what I'm actually trying to show you is that in some cases, in many cases actually, instead of having to do like what I did there and case split on types, on variables with types, you can just use a computational induction and hypothesis, and it will do the splitting for you. And this proof that I'll do now will demonstrate that to you. So firstly, I will just do the induction. So I'll do the induction normally. So on the tree, because this function is a primitive recursive function, and then I will show you how complicated the proof is, and then how to avoid the complications. Okay. So so we want to show that this pretty, basically the output of this function is unique. So it means that if two functions, if two trees have the same predicate ranking, then they are the same trees. Okay, so let's do that. So by default, we do the proof by induction on T, because as I said earlier in the earlier tutorials, that if the function is primitive recursive on a data type, then you just do the induction on the variable of that data type. Okay, so here we have that, and then let's try auto, and it doesn't work. So here we need to do case splitting on T prime, because when we do case splitting on T prime, let's just focus on the first subgoal. If we do case splitting on T prime, what we will have is the leaf case, and then the subgoal will be okay for that case, and then you will also have the case where T prime is not a leaf, and in that case what we have is a contradiction in the assumption, and accordingly the first subgoal will also be proven, because you have false implies everything. So that's the first subgoal. So in the first subgoal, I will say again for T prime, okay. No, actually, because there isn't a quantification in this case, so we don't need for. So I'll just say cases on T prime, and then apply auto. Okay, that's done. The next subgoal, I will also try, well, it failed when we applied auto the first time, but I will try and apply auto just to see, to show you. Okay, so now we applied auto here, and yeah, so firstly we need to generalize induction hypothesis, because here we have this this appending of the many lists equal to pretty T prime, while in the induction hypothesis we only have the one pretty printing of one tree equals pretty printing of T prime. So we will need to do that to get the induction hypothesis to apply, and that will cause us, then now we have a quantification over T prime, that's why we need to have 4 T prime. Okay, the second subgoal we will need to have also 4 T prime, well, not only for t prime, but let's see what the variables are. T1, 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 x2, t2, and t prime. Okay. Say t1, x, t2, and t prime. Okay. So now we have a better vision of what's going on. And now again, we need to do the case split on t prime. And then when we do the case split on t prime, we'll have t1 and we'll have that as components of t1 and t2, and the induction hypothesis will say that this will work. The induction hypothesis basically will say that t1. Well, let's just do the case split, and then I'll show you on that. Cases on t prime. Okay, so now we have t prime is empty, and that the first sub goal will be gone because you cannot have empty equals that, equals a tree with data yet. And the second sub goal will be that, and we have here, what we have here is so x21 and x23 are the two subtrees, okay, and then we say then we apply O2, and then we see, okay, so the pretty printing now of x. So we need to prove that t1 equals x21 here. So here we have, we need to show that we need to conclude something about x21, which is the first, which is this, which is the left subtree, and and that the induction hypothesis still is not strong enough because we only have here we have pretty of t1 concatenated to something equals pretty of something else concatenated to something else, but the induction hypothesis only says pretty of t1 and that's it. So we need to actually strengthen this lemma by adding a suffix to the pretty printing of a tree. So instead we say this. So the pretty printing of any tree appended to a list x's, and the pretty printing of any tree appended to any y's is going to be if we have this equality, then we have t and t prime are equal, and I think this should be true. This should hold. Okay, so now what we have there, we need to generalize the x's because we basically want to substitute that entire thing for the x's there. Okay, and then we get that. So let's generalize the x's and see. Okay, that still didn't work. And just x's and y's. Quantify otherwise. So I think this should go with a fast force call or a force call. Okay, so it's still. So what do we need there? Yeah, we need to generalize over y's as well, of course, because we need to instantiate. We need to substitute this for that in order for the induction hypothesis to work. So y's. So let's see now. So the first sub goal is gone, and I think that the second one should also be gone. So let's look at it. T2 equals 23, and this is T2. And so here we need two steps actually. We need to two logical steps. Let me just take a risk and try force and see if it will do it. Yeah, it did it. So the reason it did it was that okay, so from this one we know that T1 equals x21, and then we have a lemma that says that if two lists are appended, so we probably have a lemma that says, I'll just write it in the paper quickly because I don't want to spend much time on explaining why force did it. But we also have a lemma that says, probably we have a lemma that says x concatenated with y's equals x is prime concatenated with z's. Or actually no, x's appended with y's and x's appended with z's are equal, then this means that y's equal z's. So when we have this lemma, we have it somewhere in the simp. We can just do it by find theorem. So force was able to do the two reasoning steps. Firstly, saying that that this one is equal to that one, okay, using the first induction hypothesis, and then the second one is equal to the second one using this lemma, and then using the second induction hypothesis, was able to say that pretty T2 and pretty X21 are about the same. Okay. So anyway, so that's the proof. Okay. So let me quickly try and find this lemma that must have been used by force. So I'll just say x's appended to something equals x's appended to something as well. Yeah, and that's the lemma. So probably use that. Okay, so let me show you a clearer version of that proof. So anyway, so the idea here is that you need to split, you need to reason about both trees when they're both leaves and not leaf and not leaves. Okay. So one way to automatically do that is to basically do a simultaneous induction on both T and T prime. And what that means is that you will have an induction hypothesis that looks like this. So go to the paper. So you have an induction hypothesis that looks like this. So if you so you want to prove some predicate on T1 and T2, any T1 and T2. Okay, so in order for you to prove that predicate, you need to prove the predicate for the case when both are empty. So I'll just use that for empty 3. So when both are empty, and then you need to prove that a predicate when one of them is empty and the second one is not empty. So I'll just use T1 to they're not empty, and then when the first one is empty and the second one is not empty, and the last one, which is the most interesting case, to show that if you have an induction hypothesis that says P of the left-hand sides, okay, so let me just say L1 and L2, and another induction hypothesis that P of R1 and R2, then we have the interpredicate applying to the tree formed by L and some A, L1 and some A and some and R1. Okay, so L1 A R1, and that predicate, the second argument of the predicate will be L2 A2 and R2. Okay, so we need an induction hypothesis like that, and basically we need an induction principle like that, and that will allow us to reason about the cases where both are leaves and one is a leaf and one is not, and one is a leaf and one is not, and when both of them are not leaves. this kind of reasoning we were trying to emulate with the cases split, but now we'll do it in a cleaner way. So I'll just define. So we can either directly prove that induction principle actually as a theorem, or we can just define a function that that takes two trees and does recursion on both of them simultaneously. Any function. So I'll just define the function that is suggested in the sheet here, the function that checks if two trees have the same structure. Okay. So two trees of any. So it's just a dummy function. So we need to define any function that takes two trees and does recursions on them simultaneously. So I will just say here this function should be taking tree to the leaf. I'll just say false or true or whatever. It doesn't make a difference what we say in the function. The most important thing is that it should be doing the recursion on both trees. So LAR. Actually, no, I'll just do it L1, A1, R2. And L2, A2, sorry, that should be R1, okay. And then it calls itself, the most important thing is that it calls itself recursively, does a recursive call that follows exactly that pattern there, okay. So it will call itself, for example, on bin 3, 2, and L1, and L2. So this is to get an induction hypothesis that looks like the one that I want there. And let's say we just return this and that, and recursive call on the R's instead of the L's. Okay. So I think we need some parentheses there. So the most important thing is the induction hypothesis that comes out of this thing. So bin 3 to induct. Okay. So that's the induction hypothesis that we need that I was describing, and that does the case splitting for us whenever we're trying to prove any predicate about any two trees. Okay. It doesn't matter what you put here. You can just say and. You can say or. It doesn't really matter. Okay, so I will do the same proof. I'll prove the same theorem, the same lemma here. This actually is an auxiliary lemma for the main theorem. The main theorem will just be an instantiation of x's and y's with empty, but that's not the point of the exercise anyway. So t and t prime, and okay, and then rule bin underscore 3 to induct. Okay, so now look at this. This is exactly what we wanted. So we wanted all the four cases on when one is a leaf, the other one is not, when the other is a leaf and the first is not, and both are not leaves. Okay, and then we try and apply O2. No, we'll need the force as well. So, because it is the same logic as the step up there, okay? So it's all done. So you can just say apply force plus. Okay? So that is why we would, that's one way to avoid these case splits, to get better induction principles, okay? Either by defining functions or proving the induction principle that you want as a theorem. Okay, so that's it for today. Thank you very much for listening.